On February 14, 1990, a spacecraft floating more than 6 billion kilometers from the Sun turned its camera back toward home. The image it captured showed Earth as a single pixel, a pale blue dot suspended in a beam of scattered sunlight. From that distance, our world occupied less than 1 pixel of the photograph. Everything humanity has ever known, every ocean, every mountain, every city, every forest, existed within that minuscule point of light. The spacecraft was Voyager 1, launched on September 5, 1977, originally designed to study Jupiter and Saturn. By 1990, it had completed its primary mission and was departing the solar system entirely. The decision to turn its cameras around for one final portrait required years of discussion. Many engineers worried about the risk of pointing the instruments so close to the Sun. The cameras had already been scheduled for permanent shutdown to conserve power for the long journey into interstellar space. Voyager 1 began its journey from Cape Canaveral in Florida, carrying instruments designed to study the outer planets during a rare alignment that occurs only once every 176 years. This alignment allowed a single spacecraft to visit multiple planets using gravity assists, where each planet's gravity would accelerate the spacecraft and redirect it toward the next destination. The mission planners had calculated trajectories with extraordinary precision, accounting for the gravitational influence of each planet, the spacecraft's momentum, and the need to position Voyager for optimal scientific observations. The spacecraft itself measured about 3.6 meters tall and weighed approximately 722 kilograms at launch. Its most distinctive feature was its large dish antenna, 3.7 meters in diameter, which would be used to transmit data across billions of kilometers back to Earth. The antenna had to maintain precise pointing toward Earth even as the spacecraft tumbled through space, requiring sophisticated attitude control systems and star trackers that could lock onto guide stars to determine the spacecraft's orientation. Voyager 1 carried two types of cameras: a narrow-angle camera with a 1500mm focal length for detailed imaging of specific targets, and a wide-angle camera for capturing broader scenes. Both were Vidicon cameras, a technology similar to old television cameras, which recorded images by scanning electron beams across a photoconductive surface. The images were stored temporarily on an onboard tape recorder, then transmitted to Earth at a painstakingly slow rate due to the vast distances involved and the limited power available to the spacecraft's transmitter. Power for the spacecraft came from 3 radioisotope thermoelectric generators, or RTGs, which converted heat from the radioactive decay of plutonium-238 into electricity. At launch, these generators produced approximately 470 watts of electrical power. Over time, as the plutonium decayed, power output gradually decreased, a process that continues today. By 1990, power had declined enough that mission managers had to make difficult decisions about which instruments to keep operating and which to shut down to conserve energy for the most critical systems. The mission had already achieved extraordinary success. Voyager 1 made its closest approach to Jupiter on March 5, 1979, capturing unprecedented images of the giant planet's turbulent atmosphere, discovering active volcanoes on Jupiter's moon, Io, and revealing intricate details of Jupiter's ring system. The spacecraft then continued to Saturn, making its closest approach on November 12, 1980. At Saturn, Voyager 1 provided the first detailed images of the planet's magnificent ring system, discovered new moons, and studied Saturn's largest moon, Titan. which has a thick atmosphere and complex organic chemistry on its surface. After the Saturn encounter, Voyager 1's trajectory carried it upward out of the plane of the solar system at an angle of about 35 degrees. It would never encounter another planet. Its primary mission was complete, and many of its instruments were no longer needed for the journey ahead into interstellar space. The cameras, in particular, had no further targets to photograph. There would be no close-up views of distant moons or planets, no detailed studies of ring systems or atmospheric features. The cameras were simply consuming power that could be better used elsewhere. Carl Sagan, the astronomer and science communicator, first proposed the idea in 1980. He understood that the scientific value would be minimal. From such vast distance, Earth would reveal no geographic features, no weather patterns, no signs of civilization. But he recognized something else: the philosophical weight of seeing ourselves from the ultimate outside perspective. He persisted through 8 years of proposals, navigating bureaucratic resistance, limited resources, and the understandable caution of mission planners who had brought Voyager so far without failure. Finally, in 1989, approval came. The imaging sequence was planned by Carolyn Porco and Candy Hansen, scientists who calculated the precise exposures needed to capture Earth without overwhelming the camera sensors. On that Valentine's Day in 1990, commands sent from Earth reached Voyager 1 after traveling for more than 5 hours at the speed of light. The spacecraft executed the sequence at precisely 4:48 GMT. It captured 60 frames in total, creating what the Voyager team called the family portrait of the solar system. Earth appeared in 3 of those frames, each taken through a different color filter: blue, green, and violet. The exposure times were 0.72 seconds, zeros, 0.48 seconds, and 0.72 seconds respectively. When the 3 frames were combined, they produced the pale blue dot image. The streaks of light crossing the photograph are not cosmic phenomena, but artifacts from sunlight scattering within the camera itself, the result of pointing the instrument within a few degrees of our star. The data traveled back to Earth through the Deep Space Network, arriving in stages between March and May of 1990. Each frame contained 640,000 pixels. Earth occupied just 12/100ths of a single pixel. Candy Hansen, the first person to see the returned image, later recalled a moment of panic when she couldn't immediately spot our world against the darkness. The beam of scattered light had made Earth harder to find, not easier. When she finally located that pale point, the relief was profound. The photograph exists because of persistence, calculation, and a willingness to see ourselves differently. It required technology that could function across billions of kilometers of space, commands that traveled for hours, and patience to wait months for confirmation. It asked humanity to look at itself from a perspective no human eye had ever witnessed directly. What we saw was not our familiar globe of blues and greens and whites, but something smaller: a dot, a pixel, a fragment. This image, this pale blue dot, has become one of the most recognized photographs in the history of space exploration, not for what it reveals about planetary science, but for what it suggests about perspective, about scale, about the nature of our existence in an incomprehensibly vast universe. And yet, despite appearing so small in that photograph, Earth itself is substantial, complex, active, and precisely calibrated to support the phenomenon we call life. Earth measures 12,742 kilometers in diameter at the equator. This equatorial diameter is slightly larger than the polar diameter, which spans 12,714 kilometers. The difference of 28 kilometers exists because Earth is not a perfect sphere, but an oblate spheroid, a shape created by the planet's rotation. As Earth spins, centrifugal force causes the equatorial region to bulge outward slightly, while the polar regions remain comparatively flattened. This rotation occurs once every 23 hours and 56 minutes, which is the length of one sidereal day. The familiar 24-hour day we use in daily life is slightly longer because Earth must rotate a bit extra to bring the Sun back to the same position in the sky, accounting for our orbital movement around the Sun. This distinction between sidereal and solar time reflects the complex dance between rotation and revolution, between spinning and orbiting. The planet's mass amounts to 5.97 times 10 to the 24th power kilograms. Written out, this number is 5,972 billion trillion kilograms. Such a mass creates gravitational acceleration at the surface of 9.8 meters per second squared, the force that holds the atmosphere in place, that pulls rain from clouds, that keeps oceans in their basins and prevents them from drifting away into space. Earth's volume measures 1.083 times 10 to the 12th cubic kilometers. If you could somehow hollow out this volume and fill it with smaller Earths, you would need approximately 50 Earths the size of Mercury, or nearly 1,300 Earths the size of the Moon. Volume relates to density, and Earth's average density of 5.5 grams per cubic centimeter makes it the densest planet in our solar system. This density comes from the iron-nickel core at the planet's center, a region where pressures exceed 3 million times atmospheric pressure and temperatures rival the surface of the Sun. The core exists in two parts: a solid inner core with a radius of approximately 1,200 kilometers and a liquid outer core extending to a radius of about 3,485 kilometers. Above the core lies the mantle, a layer of hot, slowly flowing rock that comprises most of Earth's volume. The mantle extends from the core mantle boundary to within 30 to 50 kilometers of the surface, depending on location. Finally, the crust, the thin, solid outer layer where we live, varies from 5 to 70 kilometers thick. Oceanic crust is generally thinner and younger, formed continuously at mid-ocean ridges. Continental crust is thicker and older, carrying the mountain ranges, plains, and plateaus that we think of as land. The total surface area of Earth measures approximately 510 million square kilometers. Of this expanse, about 71% is covered by water, leaving roughly 29% as land. This distribution is not uniform. The Northern Hemisphere contains significantly more land than the Southern Hemisphere, with the concentration of continents creating what geographers sometimes call the land hemisphere, centered roughly on Western Europe. From pole to pole, Earth's circumference measures approximately 40,008 kilometers. From this measurement came the original definition of the meter, 1/10,000,000th of the distance from the equator to either pole. The equatorial circumference is slightly longer at 40,075 kilometers, again reflecting the oblate spheroid shape. If you could walk around Earth at the equator, maintaining a steady pace of 5 kilometers per hour without stopping, the journey would take approximately 334 days. But Earth's physical dimensions tell only part of the story. The planet is not a static rock, but a dynamic system, constantly reshaping itself through processes that operate on timescales from seconds to billions of years. Tectonic plates drift across the surface at rates measured in centimeters per year, the same speed at which fingernails grow. Over millions of years, these slow movements create mountains, trigger earthquakes, generate volcanic eruptions, and recycle the crust back into the mantle at subduction zones. Water circulates through the planet in the hydrologic cycle, evaporating from oceans, condensing into clouds, falling as precipitation, flowing through rivers and underground aquifers, and returning to the sea. The atmosphere circulates in vast convection cells, redistributing heat from the tropics toward the poles, creating weather patterns and climate zones. The magnetic field, generated by convection currents in the liquid outer core, extends far into space, creating a protective bubble that shields the surface from harmful solar radiation. These processes interact, overlap, and influence each other in ways that create stability over geological time. The carbon cycle regulates atmospheric carbon dioxide, concentrations through volcanic outgassing, chemical weathering of rocks, and the burial of organic matter in sediments. The water cycle moderates temperature extremes and distributes fresh water across the continents. The magnetic field protects the atmosphere from erosion by the solar wind, preventing Earth from following the same path as Mars, which lost most of its atmosphere after its magnetic field weakened billions of years ago. Earth's size places it fifth among the planets, larger than Mercury, Venus, and Mars, but far smaller than the gas giants Jupiter, Saturn, Uranus, and Neptune. This size is significant. A planet much smaller would have insufficient gravity to retain a substantial atmosphere. A planet much larger might retain too much hydrogen and helium from its formation, becoming a gas giant rather than a rocky world with a solid surface. Earth's size sits in a range that permits the existence of a stable atmosphere, liquid water on the surface, and geological activity driven by internal heat. The mass of Earth determines how much material could accumulate during the planet's formation 4.5 billion years ago. In the early solar system, the protoplanetary disk contained regions of different composition. Close to the Sun, where temperatures were high, only materials with high melting points could condense into solid form, metals and silicates. Farther out, beyond what astronomers call the frost line, water ice could also condense, allowing planets to accumulate more mass. Earth formed in the inner region, accreting from rocky and metallic materials, while Jupiter and the other gas giants formed beyond the frost line, where ice allowed them to grow much more massive. The internal structure of Earth, with its iron core, rocky mantle, and thin crust, reflects the process of differentiation that occurred early in the planet's history. Initially, Earth was probably more homogeneous, with metals and silicates mixed throughout. But as the planet grew and heat from impacts and radioactive decay accumulated, materials began to melt and separate according to density. Iron, being dense, sank toward the center, forming the core. Lighter silicates rose toward the surface, forming the mantle and eventually the crust. This differentiation released tremendous amounts of gravitational potential energy, further heating the planet and ensuring that Earth's interior has remained hot and geologically active for billions of years. The precise balance of Earth's composition, its distance from the Sun, its size, its rotation rate, and the presence of a large moon all contribute to conditions that permit liquid water to exist on the surface. This liquid water, in turn, has shaped nearly every aspect of Earth's geology, climate, and biology. Water weathers rocks, transports sediments, drives plate tectonics through its role in creating and recycling oceanic crust, and provides the medium in which life as we know it can exist and evolve. Surrounding Earth's solid surface is a layer of gas held in place by gravity. This atmosphere extends from sea level to approximately 10,000 kilometers above the surface, though most of its mass is concentrated in the lowest layers. The atmosphere serves multiple functions. It distributes heat around the planet, shields the surface from harmful radiation, enables weather and climate, and provides the oxygen that most complex life requires for respiration. The composition of this atmosphere is predominantly nitrogen, which makes up 78.08% of dry air by volume. Oxygen accounts for 20.95%. Argon, a noble gas that does not readily react with other elements, comprises 0.93%. Carbon dioxide, despite its significance for climate and photosynthesis, represents only about 0.04% of the atmosphere. Water vapor, though not typically included in measurements of dry air, composition, because its concentration varies greatly with location and time, can account for up to 4% of the atmosphere in humid tropical regions. This composition is not the atmosphere Earth was born with. The original atmosphere, formed from gases released during the planet's accretion, would have been lost, stripped away by solar wind before Earth's magnetic field fully developed, or blown off by the enormous impact that likely created the Moon. The secondary atmosphere developed gradually from volcanic outgassing, as gases dissolved in the mantle were released through volcanic eruptions. This early secondary atmosphere probably contained mostly water vapor, carbon dioxide, nitrogen, and sulfur compounds, with little to no oxygen. The presence of abundant oxygen in today's atmosphere is the direct result of life. Beginning about 2.4 billion years ago, photosynthetic bacteria began producing oxygen as a waste product. Initially, this oxygen reacted with dissolved iron in the oceans, creating vast deposits of iron oxide that geologists call banded iron formations. Once the oceans were saturated, oxygen began accumulating in the atmosphere, eventually reaching concentrations high enough to support aerobic respiration and the evolution of complex multicellular organisms. The atmosphere is structured in layers defined by how temperature changes with altitude. The lowest layer, the troposphere, extends from the surface to approximately 12 kilometers in altitude at mid-latitudes, though it can reach 18 kilometers at the equator and compress to about 6 kilometers at the poles. The troposphere contains about 75 to 80% of the atmosphere's total mass and nearly all of its water vapor. Temperature in the troposphere decreases with altitude at an average rate of about 6.5 degrees Celsius per kilometer, a phenomenon caused by the decreasing air pressure allowing air to expand and cool. At the top of the troposphere lies the tropopause, a boundary beyond which temperature stops decreasing with altitude. Above the tropopause is the stratosphere, extending from roughly 12 to 50 kilometers above the surface. In the stratosphere, temperature actually increases with altitude, an inversion caused by the absorption of ultraviolet radiation by ozone molecules. Ozone, a molecule composed of 3 oxygen atoms, forms when ultraviolet light splits oxygen molecules into individual atoms, which then recombine with other oxygen molecules. This process absorbs high-energy ultraviolet radiation that would otherwise reach the surface and damage living tissue. The ozone layer is not a discrete shell, but a region of enhanced ozone concentration, typically found at altitudes between 15 and 35 kilometers. Despite its critical importance for shielding life from ultraviolet radiation, the ozone layer is quite thin. If you could compress all the ozone in the atmosphere into a layer, at sea level pressure, it would be only about 3 millimeters thick. Above the stratosphere, Separated by the stratopause boundary, lies the mesosphere, extending from approximately 50 to 85 kilometers above the surface. In the mesosphere, temperature again decreases with altitude, reaching the coldest temperatures found anywhere in Earth's atmosphere, sometimes dropping below -90 degrees Celsius. The mesosphere is where most meteors burn up as they enter Earth's atmosphere, creating the streaks of light we call shooting stars. The friction between the meteor and the sparse air molecules generates enough heat to vaporize the incoming rock. The thermosphere begins at the mesopause and extends from about 85 to 600 kilometers above Earth's surface. Here, temperature increases dramatically with altitude, potentially reaching 2,000 degrees Celsius or more, though the air is so thin that this heat would not feel warm to an exposed object. The thermosphere is where the aurora occurs, created when charged particles from the Sun follow Earth's magnetic field lines and collide with atmospheric molecules, causing them to emit light. The International Space Station orbits within the thermosphere at an altitude of approximately 420 kilometers. Finally, the exosphere, the outermost layer, extends from approximately 600 kilometers to 10,000 kilometers, gradually transitioning to the near vacuum of space. In the exosphere, atmospheric particles are so sparse that they can travel hundreds of kilometers without colliding with another particle. Some particles in the exosphere have enough velocity to escape Earth's gravitational pull entirely, slowly leaking away into space over geological time. The atmosphere's ability to retain heat through the greenhouse effect is essential for maintaining Earth's habitable temperature. Without an atmosphere, Earth's average surface temperature would be approximately -18 degrees Celsius, well below the freezing point of water. The current average temperature of about 15 degrees Celsius exists because greenhouse gases in the atmosphere, particularly water vapor, carbon dioxide, and methane, absorb infrared radiation emitted by Earth's surface and re-radiate some of it back downward. This process traps heat that would otherwise escape directly to space. The balance of incoming solar radiation and outgoing infrared radiation determines Earth's energy budget and average temperature. Approximately 29% of incoming solar radiation is reflected back to space by clouds, atmospheric particles, and Earth's surface. About 23% is absorbed by the atmosphere itself, primarily by water vapor, clouds, and ozone. The remaining 48% reaches the surface, where it is absorbed and eventually re-radiated as infrared radiation. The atmosphere absorbs much of this infrared radiation and re-radiates it in all directions, creating the greenhouse effect that warms the surface. Atmospheric circulation redistributes this heat around the planet. The equatorial regions receive more solar energy per unit area than the polar regions because the sun's rays strike more directly there. This creates a temperature gradient that drives atmospheric and oceanic circulation. Warm air rises at the equator, creating a region of low pressure. As this air rises, it cools and releases moisture, creating the heavy rainfall characteristic of tropical regions. The now dry air moves toward the poles at high altitude, eventually descending in the subtropical regions around 30 degrees latitude, creating the world's major deserts. This circulation pattern, called a Hadley cell, is one of several large-scale atmospheric circulation systems that distribute heat and moisture around the planet. The Coriolis effect, caused by Earth's rotation, deflects moving air masses to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection creates the prevailing wind patterns. the trade winds in the tropics, the westerlies in mid-latitudes, and the polar easterlies near the poles. These wind patterns, combined with the distribution of land and ocean, create the complex weather systems and climate zones we observe. The atmosphere's pressure decreases exponentially with altitude, following a pattern described by the barometric formula. At sea level, atmospheric pressure averages 1,013.25 millibars, equivalent to the weight of a column of air extending from the surface to the top of the atmosphere. By an altitude of 5.6 kilometers, pressure has decreased to half its sea level value. By 16 kilometers, it has decreased to 1/10. The rapid decrease in pressure with altitude reflects the compressibility of air and the fact that air near the surface is compressed by the weight of all the air above it. This atmosphere, thin as it is compared to the diameter of the planet itself, makes Earth habitable. It moderates temperature extremes between day and night, protects the surface from harmful radiation, enables the water cycle, provides pressure that allows water to remain liquid at surface temperatures, and creates the weather patterns that distribute heat and moisture around the world. The Moon, lacking an atmosphere, experiences temperature swings from approximately 123 degrees Celsius in sunlit regions to minus 173 degrees Celsius in permanently shadowed craters. Earth's atmosphere prevents such extremes, creating a far more stable thermal environment. Water covers approximately 70.8% of Earth's surface, creating the distinctive blue appearance that gives our planet its color when viewed from space. The total volume of water on Earth is approximately 1.386 billion cubic kilometers. Of this vast quantity, 97.5% exists as salt water in the oceans, while only 2.5% is fresh water. Of the fresh water, approximately 68.7% is locked in ice caps and glaciers, 30.1% exists as groundwater, and only about 1.2% is surface water in lakes, rivers, and swamps. The oceans themselves are divided by convention into 5 major basins: the Pacific, Atlantic, Indian, Arctic, and Southern Oceans. The Pacific Ocean is by far the largest, containing more water than all the other oceans combined and covering an area greater than all of Earth's land surface. The average depth of all oceans is approximately 3,700 meters, though the deepest point in the Mariana Trench reaches nearly 11,000 meters below sea level. Ocean water contains dissolved salts with an average concentration of about 35 parts per thousand, or 3.5%. This salinity results from billions of years of weathering continental rocks, which releases ions that rivers carry to the sea. Evaporation removes water, but leaves the salts behind, gradually concentrating them in the ocean. The specific composition of seawater is remarkably constant. Sodium and chloride ions dominate, forming common salt, but seawater also contains magnesium, sulfate, calcium, potassium, and many other dissolved elements in smaller concentrations. Water's unique physical properties make it essential for life as we know it. It exists in all 3 phases: solid, liquid, and gas, at temperatures commonly found on Earth's surface. Water has an unusually high specific heat capacity, meaning it can absorb or release large amounts of heat with relatively small changes in temperature. This property allows oceans to store vast quantities of heat, moderating coastal climates and driving ocean circulation. Water is also unusual in being less dense as a solid than as a liquid. Ice floats on water, a property that prevents lakes and oceans from freezing from the bottom up and killing all aquatic life during winter. The hydrologic cycle continuously circulates water between the oceans, atmosphere, land, and living organisms. Approximately 500,000 cubic kilometers of water evaporates from the oceans each year. Most of this water vapor condenses and falls back to the ocean as precipitation, but about 40,000 cubic kilometers falls on land. This fresh water supports terrestrial ecosystems, replenishes rivers and lakes, and infiltrates into the ground to recharge aquifers. Eventually, through surface runoff and groundwater flow, this water returns to the ocean, completing the cycle. Ocean currents transport heat around the planet, playing a crucial role in regulating climate. Surface currents are driven primarily by wind, with the pattern of currents largely determined by the prevailing wind patterns and the Coriolis effect. The Gulf Stream, for example, carries warm water from the tropical Atlantic northward along the east coast of North America and then across the Atlantic to Europe, moderating the climate of Western Europe and making it significantly warmer than other regions at similar latitudes. Deep ocean currents, driven by differences in water density caused by variations in temperature and salinity, form a global circulation pattern sometimes called the thermohaline circulation or ocean conveyor belt. Cold, dense water sinks in the North Atlantic and Antarctic, creating deep currents that flow toward the equator. This deep water eventually rises back to the surface through upwelling, completing a circulation pattern that can take 1,000 years or more. This deep circulation plays a vital role in distributing heat and nutrients throughout the ocean and in absorbing carbon dioxide from the atmosphere. Fresh water on land exists in various reservoirs with vastly different residence times. Water in the atmosphere has an average residence time of about 9 days. Water in rivers flows to the sea in a matter of weeks. Groundwater in shallow aquifers might remain underground for years or decades, while water in deep aquifers can persist for thousands of years. Water in glaciers can remain frozen for tens of thousands of years. These different residence times mean that water cycles through the hydrologic system at many different rates, creating a complex dynamic system. Lakes contain the majority of Earth's surface fresh water. The African Rift Valley holds several large lakes, including Lake Tanganyika and Lake Malawi. The North American Great Lakes contain approximately 21% of the world's surface fresh water by volume. Lake Baikal in Russia, the world's deepest lake at 1,642 meters, contains as much water as all 5 Great Lakes combined, despite covering a much smaller surface area. These lakes serve as reservoirs that moderate local climate, support unique ecosystems, and provide fresh water for human use. Rivers, though containing a small fraction of Earth's total water, play a disproportionately important role in shaping landscapes and supporting life. Rivers erode mountains, transport sediment, carve canyons, and deliver nutrients and fresh water to the oceans. The Amazon River discharges approximately 200,000 cubic meters of water per second into the Atlantic Ocean, accounting for roughly 20% of all river water reaching the oceans worldwide. This massive flow creates a plume of fresh water that extends hundreds of kilometers into the Atlantic. Groundwater, hidden beneath the surface, represents the largest reservoir of liquid fresh water on Earth. Aquifers are underground layers of permeable rock or sediment that store and transmit groundwater. Some aquifers are recharged relatively quickly by infiltrating precipitation, while others, called fossil aquifers, contain water that infiltrated thousands or even millions of years ago and are not being replenished on human timescales. The Ogallala Aquifer beneath the Great Plains of North America, for example, contains water deposited during the last ice age, and current extraction rates far exceed recharge rates. Ice, the solid form of water, exists primarily in the Antarctic and Greenland ice sheets, which together contain approximately 99% of Earth's ice. If all this ice were to melt, sea level would rise by approximately 70 meters, inundating many of the world's coastal cities. During ice ages, when more water is locked in ice sheets and glaciers, sea level drops. At the peak of the last ice age, approximately 20,000 years ago, sea level was about 120 meters lower than today, exposing land bridges that allowed human migration between continents. The distribution of water on Earth's surface creates distinct climate zones and ecosystems. Tropical rainforests, supported by abundant rainfall, harbor extraordinary biodiversity. Deserts, where evaporation exceeds precipitation, challenge life with aridity. Temperate regions with moderate precipitation and seasonal variation support agriculture and dense human populations. The polar regions, cold and dry, support specialized ecosystems adapted to extreme conditions. Water's role in Earth's habitability extends beyond climate regulation and ecosystem support. Water is the universal solvent in biological systems, the medium in which biochemical reactions occur. Life requires liquid water because only in liquid form can water dissolve and transport nutrients, remove waste products, and allow the molecular interactions necessary for metabolism. The presence of liquid water on Earth's surface, maintained by the planet's temperature and atmospheric pressure, is perhaps the single most important factor enabling the existence of life. Earth generates a magnetic field that extends far into space, creating a region called the magnetosphere. This magnetic field originates deep within the planet, in the liquid outer core where convection of molten iron generates electrical currents. These currents, in turn, produce the magnetic field through a self-sustaining process called a geodynamo. The field extends from Earth's interior out into space, creating a protective bubble that shields the surface from the solar wind and cosmic radiation. At Earth's surface, the magnetic field strength ranges from approximately 25 to 65 microteslas, depending on location. The field resembles that of a bar magnet tilted about 11 degrees from Earth's rotational axis. The North Magnetic Pole, where field lines point downward, is currently located in the Canadian Arctic, slowly drifting northwest at a rate of several kilometers per year. The South Magnetic Pole is located in Antarctica. These magnetic poles should not be confused with the geographic poles, which are defined by Earth's axis of rotation. The Earth magnetic field's configuration is complex. Near the surface, it approximates a dipole field, with field lines emerging from the South Magnetic Pole and entering at the North Magnetic Pole. But farther from Earth, the field is distorted by the solar wind, a continuous stream of charged particles flowing outward from the Sun at speeds of 300 to 900 kilometers per second. On the side facing the Sun, the solar wind compresses the magnetosphere to a distance of about 10 Earth radii. On the night side, the magnetosphere is drawn out into a long tail called the magnetotail, which extends hundreds of Earth radii downstream. The boundary between the magnetosphere and the solar wind is called the magnetopause. This is where the pressure of Earth's magnetic field balances the pressure of the solar wind. The magnetopause is not a solid barrier, but a dynamic boundary that moves inward and outward in response to changes in solar wind pressure. During quiet conditions, it typically sits at about 10 Earth radii on the day side. During strong solar storms, it can be pushed inward to within 6 Earth radii, bringing the boundary much closer to Earth's surface. Upstream of the magnetopause, at a distance of about 14 Earth radii, is the bow shock. This is where the supersonic solar wind encounters Earth's magnetic field and slows abruptly to subsonic speeds, similar to the shock wave that forms in front of a supersonic aircraft. The region between the bow shock and the magnetopause is called the magnetosheath, where the solar wind is compressed, heated, and deflected around Earth. The magnetosphere's most important function is protecting Earth's atmosphere from erosion by the solar wind. Mars, which lacks a global magnetic field, has lost most of its atmosphere over billions of years as the solar wind stripped away atmospheric particles. Studies comparing atmospheric loss rates between Earth and Mars during periods of similar solar wind pressure have found that Mars loses atmospheric oxygen at approximately 10 times the rate of Earth, demonstrating the protective effect of Earth's magnetic field. Within the magnetosphere are 2 donut-shaped regions of trapped energetic particles called the Van Allen radiation belts. The inner belt, located at altitudes between about 1,000 and 6,000 kilometers, contains primarily high-energy protons. The outer belt, extending from about 13,000 to 60,000 kilometers, contains mainly electrons. These belts were discovered by James Van Allen in 1958 using data from the Explorer satellites. The particles in these belts are trapped by Earth's magnetic field, spiraling back and forth along field lines and bouncing between the northern and southern hemispheres. The radiation belts pose a hazard to spacecraft and astronauts. The energetic particles can penetrate spacecraft shielding, damage electronic components, and expose astronauts to harmful radiation. Satellites orbiting in the radiation belts require special shielding and radiation-hardened electronics. The International Space Station orbits below the inner belt, avoiding the worst of the radiation, though astronauts still receive higher radiation doses than people on Earth's surface. Aurora, the spectacular light displays visible at high latitudes, result from the interaction between the solar wind and Earth's magnetosphere. When the solar wind's magnetic field has a component pointing opposite to Earth's field, a process called magnetic reconnection can occur at the magnetopause. This allows some solar wind energy to enter the magnetosphere, accelerating particles along magnetic field lines toward the polar regions. When these particles collide with atmospheric molecules at altitudes of 100 to 500 kilometers, they excite the molecules, causing them to emit light. Oxygen atoms produce green and red auroral light, while nitrogen produces blue and purple. Aurora typically occur in oval-shaped regions centered on the magnetic poles, called auroral zones. These zones expand toward the equator during strong geomagnetic storms when solar wind pressure and energy input into the magnetosphere increase. The strongest storms can produce aurora visible at mid-latitudes. The aurora australis, or southern lights, occur in the southern hemisphere, mirroring the aurora borealis in the north, though they are less frequently observed because the auroral zone in the south lies mostly over ocean and the Antarctic continent. Solar storms represent the most significant space weather events affecting Earth's magnetosphere. Coronal mass ejections, or CMS, are enormous eruptions of plasma and magnetic field from the Sun's corona. When a CME reaches Earth, typically 1 to 3 days after leaving the Sun, it can compress the magnetosphere and inject large amounts of energy into the magnetotail. This energy is eventually released explosively in events called magnetospheric substorms, which accelerate particles into the auroral zones and can disrupt communication and navigation systems, damage satellites, and even affect electrical power grids on the ground. The most powerful geomagnetic storm on record, the Carrington event of 1859, caused aurora visible as far south as the Caribbean and disrupted telegraph systems worldwide. If a similar event occurred today, it could cause widespread damage to modern technological infrastructure, potentially affecting satellites, GPS navigation, power grids, and communication networks. Space weather forecasting has become increasingly important as society becomes more dependent on space-based technology. Earth's magnetic field has not remained constant over geological time. The field's strength fluctuates, and the positions of the magnetic poles drift. Most remarkably, the field occasionally reverses completely, with the north and south magnetic poles switching places. The geologic record preserved in volcanic rocks and ocean floor sediments shows that these reversals have occurred hundreds of times over Earth's history, though the interval between reversals is highly irregular, ranging from tens of thousands to millions of years. The last reversal occurred approximately 780,000 years ago. During a reversal, which typically takes several thousand years to complete, the magnetic field weakens considerably, potentially to less than 10% of its normal strength. A weakened field would provide less protection from cosmic radiation, though the atmosphere would still shield the surface from the most harmful radiation. There is no evidence that previous reversals have caused mass extinctions, suggesting that life can survive these events, but the effects on modern technology during a reversal are uncertain and potentially concerning. The magnetosphere, invisible to our eyes but revealed through scientific instruments, represents one of Earth's essential protective systems. It deflects the solar wind, traps harmful radiation in the Van Allen belts, creates the aurora, and prevents the slow erosion of our atmosphere into space. Without this magnetic shield, Earth might have followed the path of Mars, losing its atmosphere and surface water over billions of years, transforming from a living world into a cold, dry, barren planet. Earth orbits the Sun at an average distance of 149.6 million kilometers, a distance defined as 1 astronomical unit. This measurement serves as a fundamental yardstick in astronomy, used to describe distances within the solar system and beyond. Light from the Sun takes approximately 8 minutes and 19 seconds to cross this distance, meaning that when we look at the Sun, we see it as it was slightly more than 8 minutes ago. Earth's orbit is not a perfect circle, but an ellipse with an eccentricity of 0.0167. This low eccentricity means the orbit is very nearly circular, with the difference between the closest and farthest points amounting to only about 5 million kilometers. At perihelion, the point of closest approach to the Sun, which occurs around January 3rd each year, Earth is approximately 147.1 million kilometers from the Sun. At aphelion, the most distant point, which occurs around July 4th, Earth is approximately 152.1 million kilometers away. The fact that perihelion occurs in January, during Northern Hemisphere winter, often surprises people in northern latitudes who assume that winter must occur when Earth is farthest from the Sun. This demonstrates that Earth's distance from the Sun is not the primary cause of seasons. The seasons result instead from Earth's axial tilt. The planet's rotation axis is tilted approximately 23.4 degrees from perpendicular to its orbital plane. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences summer, while the southern hemisphere, tilted away, experiences winter. 6 months later, the situation reverses. This axial tilt causes the sun's apparent path through the sky to vary throughout the year. At the summer solstice in the northern hemisphere, around June 21st, the sun reaches its highest point in the sky, and day length is at its maximum. At the winter solstice, around December 21st, the sun reaches its lowest point, and day length is at its minimum. At the equinoxes, around March 20th and September 22nd, day and night are approximately equal in length worldwide. Earth travels around the sun at an average orbital velocity of 29.78 kilometers per second. At this speed, Earth completes one full orbit in approximately 365.256 days, which defines 1 year. The extra quarter day accumulates over 4 years to create nearly a full day, which is why we add a leap day, February 29th, every 4th year to keep our calendar synchronized with Earth's orbit. The orbital velocity varies slightly as Earth moves along its elliptical path. At perihelion, when Earth is closest to the Sun and gravity is slightly stronger, orbital velocity increases to approximately 30.3 kilometers per second. At aphelion, velocity decreases to approximately 29.3 kilometers per second. These velocity changes mean that Earth spends slightly less time in the portion of its orbit where it is closest to the Sun. For the Northern Hemisphere, this means winter is slightly shorter than summer by about 5 days. The plane of Earth's orbit around the Sun is called the ecliptic. The Moon's orbit around Earth is tilted about 5 degrees relative to the ecliptic, which is why solar and lunar eclipses do not occur every month. Eclipses can only occur when the Moon crosses the ecliptic plane, and this happens only twice each year during periods called eclipse seasons. During an eclipse season, if a new moon occurs when the Moon crosses the ecliptic, a solar eclipse results. If a full moon occurs during a crossing, a lunar eclipse results. Earth's orbit is remarkably stable over timescales relevant to human civilization, but over millions of years, gravitational perturbations from other planets cause subtle changes. The eccentricity of Earth's orbit varies from nearly circular, eccentricity near zero, to slightly more elliptical, eccentricity up to 0.058, over a cycle of approximately 100,000 years. The axial tilt varies between 22.1 and 24.5 degrees over a 41,000-year cycle. The direction that Earth's rotation axis points in space slowly changes over a 26,000-year cycle called precession. These long-term orbital variations, called Milankovitch cycles, affect the distribution of solar radiation across Earth's surface and influence climate on timescales of tens of thousands of years. They are believed to be a major driver of the Ice Age cycles that have characterized Earth's climate for the past several million years. During periods when northern summer occurs at aphelion and the northern continents receive less solar radiation, ice sheets can grow, eventually leading to an ice age. When the cycles reverse, the ice sheets retreat. The stability of Earth's orbit over billions of years is remarkable, given the complex gravitational interactions between all the planets in the solar system. Mathematical studies of orbital dynamics show that while planetary orbits can remain stable over extremely long timescales, there is a very small probability of chaotic behavior that could, over billions of years, lead to significant orbital changes or even planetary collisions. However, these timescales are comparable to the remaining lifetime of the Sun as a main sequence star, meaning that Earth's orbit should remain stable for as long as the Sun continues to shine. Earth's position in the solar system, neither too close nor too far from the Sun, places it within the habitable zone, sometimes called the Goldilocks zone. This is the range of distances from a star where liquid water can exist on a planet's surface. Too close to the sun and water would evaporate, too far and it would freeze. Earth's orbit keeps surface temperatures within the range where water can exist in all three phases, enabling the complex chemistry of life. The concept of a habitable zone is somewhat simplified because a planet's temperature depends on many factors beyond just distance from its star. Atmospheric composition, cloud cover, surface reflectivity, and greenhouse gas concentrations all play crucial roles. Venus, despite being closer to the Sun than Earth, has such a thick atmosphere with such a strong greenhouse effect that its surface temperature exceeds 460 degrees Celsius, hot enough to melt lead. Mars, farther from the Sun, is cold and dry, with an average surface temperature around -60 degrees Celsius, though liquid water may have existed on its surface billions of years ago when its atmosphere was thicker. Earth's stable circular orbit, combined with its moderate rotation rate, prevents extreme temperature variations. The Moon, which has essentially no atmosphere and rotates slowly, experiences surface temperatures ranging from approximately 123 degrees Celsius in sunlit areas to -173 degrees Celsius in shadow. Earth's atmosphere and relatively rapid rotation spread heat around the planet, moderating these extremes and creating a more hospitable environment. The journey around the Sun has continued for 4.5 billion years, will continue for billions more, a predictable path through space that defines our year, marks our seasons, creates the rhythm of day and night, provides the steady input of solar energy that drives all of Earth's systems and maintains the conditions necessary for life. Earth is the only world known to harbor life. The variety of living organisms sharing this planet is staggering, though scientists disagree about the exact number of species. Conservative estimates suggest approximately 8.7 million eukaryotic species exist, though only about 1.2 million have been formally described and catalogued. More expansive estimates, particularly when including bacteria and other microorganisms, suggest the total could range from 1 billion to 1 trillion species, with the uncertainty reflecting how little we know about microbial diversity. Among animals, approximately 7.77 million species are estimated to exist, with around 953,000 described. This means roughly 87% of animal species remain unknown to science. Insects dominate animal diversity, potentially accounting for more than half of all animal species. Beetles alone may represent approximately 1/3 of all animal species, with estimates suggesting there could be several million beetle species worldwide, though only about 400,000 have been described. Plants are estimated to number around 298,000 species, with approximately 216,000 already described. Fungi, which include everything from single-celled yeasts to massive mushroom-forming organisms, may total around 611,000 species, though only about 43,000 are currently known. These numbers reflect the traditional kingdoms of life, but they exclude the vast diversity of bacteria and archaea, single-celled organisms that lack cell nuclei and may collectively represent the majority of Earth's biodiversity. Marine environments, covering more than 70% of Earth's surface, harbor approximately 2.2 million species, of which only about 250,000 have been described. The ocean's sheer volume and the technical challenges of exploring deep-sea environments mean that marine biodiversity remains largely unknown. The deep sea, in particular, likely contains vast numbers of undiscovered species adapted to the extreme conditions of high pressure, complete darkness, and cold temperatures found at depths of thousands of meters. Life exists in almost every environment on Earth where liquid water can be found. Organisms have been discovered living in boiling hot springs, in ice sheets kilometers thick, in the driest deserts, in acidic lakes, in rocks kilometers beneath the surface, and in the deepest ocean trenches. These extreme environments, once thought to be lifeless, host specialized microorganisms called extremophiles that have adapted to conditions that would be rapidly fatal to most other life forms. The distribution of biodiversity across Earth's surface is highly uneven. Tropical regions, particularly tropical rainforests, harbor exceptional diversity, with some tropical forests containing more tree species in a single hectare than exist in all of North America. Coral reefs, sometimes called the rainforests of the sea, support approximately 25% of all marine species, despite covering less than 1% of the ocean floor. The reasons for this tropical concentration of diversity are complex but relate to factors including temperature, precipitation, evolutionary history, and the area of tropical habitat. The number of individual organisms alive at any given time is beyond precise calculation, but must be incomprehensibly large. One estimate suggests that Earth may harbor 1 trillion individual species of microorganisms. The number of individual animals, plants, fungi, and other macroscopic organisms, while impossible to count directly, must number in the hundreds of quadrillions or more when considering small organisms like insects, worms, and other invertebrates. Life on Earth shares a common biochemistry. All known organisms use DNA to store genetic information and RNA to help translate that information into proteins. All use proteins built from the same set of approximately 20 amino acids. All use the same basic metabolic pathways to extract energy from nutrients. This universal biochemistry suggests that all life on Earth descends from a common ancestor that lived billions of years ago, likely a simple single-celled organism from which all subsequent diversity has evolved. The history of life on Earth spans approximately 3.5 billion years, beginning shortly after the planet's surface cooled enough to support liquid water. The first life forms were almost certainly single-celled microorganisms similar to modern bacteria. For roughly 2 billion years, life remained exclusively microbial, slowly diversifying and fundamentally changing Earth's environment by producing oxygen through photosynthesis. Oxygen, toxic to many early life forms, accumulated in the atmosphere and oceans, creating conditions that eventually allowed the evolution of complex multicellular organisms. The first animals appeared in the oceans approximately 600 million years ago, during a period called the Ediacaran. These early animals were soft-bodied and left few fossils, making them difficult to study. The Cambrian explosion, beginning around 540 million years ago, saw the rapid diversification of animal body plans, with most major groups of animals appearing in the fossil record over a relatively short geological period. Life colonized land approximately 470 million years ago, first with plants and fungi, followed later by animals. The history of life has been punctuated by mass extinction events, during which large percentages of species disappeared in geologically short time periods. The largest known extinction, at the end of the Permian period approximately 252 million years ago, eliminated roughly 90% of marine species and 70% of terrestrial vertebrate species. The extinction that ended the Cretaceous period 66 million years ago, likely caused by an asteroid impact, eliminated the non-avian dinosaurs and many other species, but created ecological opportunities that allowed mammals to diversify and eventually become dominant land animals. Despite these catastrophic events, life has persisted and diversified. The current diversity of life on Earth may be higher than at any previous time in the planet's history, though we cannot know this with certainty because the fossil record is incomplete and because microbial diversity in the past cannot be directly observed. What is certain is that Earth's biosphere is remarkably resilient, capable of recovering from even the most severe disruptions over timescales of millions of years. Humans represent just one species among millions, though our impact on the biosphere has been profound and accelerating. The current rate of species extinction, driven primarily by habitat destruction, climate change, overexploitation, and the introduction of invasive species, may be 100 to 1,000 times higher than the background extinction rate observed in the fossil record. Some biologists argue that we are in the early stages of a sixth mass extinction event, this one caused by human activity rather than natural processes. The loss of biodiversity has practical consequences beyond the intrinsic value of species. Ecosystems provide services essential to human well-being. They purify air and water, decompose wastes, pollinate crops, regulate climate, cycle nutrients, control pests, and provide resources including food, fiber, and medicines. As biodiversity declines, ecosystems may lose resilience and become less able to provide these services. Understanding and preserving biodiversity has become increasingly urgent as recognition grows that human prosperity depends fundamentally on the health of Earth's living systems. Life has shaped Earth as much as Earth has shaped life. Photosynthetic organisms produce the oxygen we breathe. Plants and other organisms influence weathering rates, affecting the carbon cycle and climate. Organisms create soil, filter water, and modify nearly every aspect of Earth's surface and atmosphere. The presence of life has made Earth fundamentally different from other planets, transforming it into a world where biological and geological processes are intimately intertwined. Earth is the third planet from the Sun in a solar system that includes 7 other major planets, 5 recognized dwarf planets, hundreds of moons, millions of asteroids, and countless comets. Among the terrestrial planets, the rocky worlds of the inner solar system, Earth is the largest and most massive. Venus, often called Earth's twin because of similar size and composition, is actually quite different, with a crushing carbon dioxide atmosphere, surface temperatures hot enough to melt lead, and no evidence of current geological activity. Mars, smaller and farther from the Sun, is cold and dry, with a thin atmosphere composed mostly of carbon dioxide. Liquid water cannot exist on Mars's surface under current conditions, though the planet shows clear evidence of ancient river valleys, lake beds, and perhaps even an ancient ocean, suggesting that Mars was once warmer and wetter billions of years ago. Mercury, the closest planet to the Sun and the smallest of the terrestrial worlds, has virtually no atmosphere and experiences extreme temperature swings between its scorching day side and frozen night side. Beyond Mars lies the asteroid belt, a region containing millions of rocky bodies ranging from dust particles to objects hundreds of kilometers across. These asteroids represent material that never coalesced into a planet, prevented from doing so by gravitational perturbations from Jupiter. The asteroid belt marks the boundary between the inner rocky planets and the outer gas and ice giants. The giant planets, Jupiter, Saturn, Uranus, and Neptune, dwarf the terrestrial worlds in size and mass. Jupiter alone contains more mass than all the other planets combined. These worlds are composed primarily of hydrogen and helium, with no solid surface in the conventional sense. They possess extensive systems of moons, many of which are larger and more geologically active than some of the terrestrial planets. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both show evidence of liquid water oceans beneath icy crusts, making them potential habitats for life. Saturn's moon Titan has a thick nitrogen atmosphere and lakes of liquid methane on its surface, creating a complex system of weather and geology driven by methane instead of water. The variety among the solar system's moons demonstrates that interesting and complex worlds exist not just among the planets, but among their satellites as well. Earth's moon is unusual in several respects. It is large relative to its parent planet, with a diameter about 1/4 that of Earth. Only Pluto's moon Charon is larger relative to its planet. The leading theory for the moon's formation, the giant impact hypothesis, suggests that a Mars-sized object struck Earth approximately 4.5 billion years ago, shortly after the solar system formed. The debris from this impact coalesced to form the moon, which explains why the moon's composition is similar to Earth's mantle but lacks significant iron, and why the moon has no substantial atmosphere or magnetic field. The moon's gravitational influence on Earth is substantial. It stabilizes Earth's axial tilt, preventing large chaotic variations that would cause dramatic climate swings. The moon creates tides in Earth's oceans, and tidal friction between Earth and the moon has slowed Earth's rotation over geological time. Billions of years ago, days were shorter, perhaps only 6 hours long. The moon has also gradually moved away from Earth as a result of tidal interactions, currently receding at a rate of approximately 3.8 centimeters per year. Earth's position in the solar system places it in a region where temperatures allow water to exist in liquid form, where the intensity of solar radiation is sufficient to drive photosynthesis, but not so intense as to strip away the atmosphere, and where the solar system's architecture has protected Earth from excessive impacts by large asteroids or comets. Jupiter's strong gravity likely helps deflect some potentially hazardous objects away from the inner solar system, though this protective effect may be overstated in popular accounts. The solar system itself is not isolated, but orbits the center of the Milky Way galaxy, a barred spiral galaxy containing hundreds of billions of stars. The Sun's orbit around the galactic center takes approximately 225 to 250 million years, a period sometimes called a cosmic year. In Earth's entire history, the solar system has completed roughly 20 such orbits. Our location in the galaxy, about 26,000 light-years from the galactic center, places us in a relatively quiet region between spiral arms, where star formation and supernova explosions are less frequent than in denser regions. The Milky Way itself is part of a larger structure called the Local Group, a collection of more than 50 galaxies dominated by the Milky Way and the Andromeda Galaxy. The Local Group is, in turn, part of the Virgo supercluster, which contains tens of thousands of galaxies. And the Virgo supercluster is one among hundreds of thousands of such superclusters in the observable universe, which extends approximately 93 billion light-years in diameter. In this cosmic context, Earth's significance is not in its size or mass or location, but in what it harbors: life, complexity, consciousness, culture, the ability to look outward and comprehend, however partially, the universe of which it is a part. The pale blue dot captured by Voyager 1 represents more than just a planet. It represents the only place we currently know where the universe has become aware of itself, where matter has organized into forms capable of wondering about their own existence and their place among the stars. Carl Sagan, reflecting on the pale blue dot photograph, wrote words that have echoed across the decades since. He pointed out that everyone you love, everyone you know, every human being who ever lived out their lives on that mote of dust suspended in a sunbeam. Every saint and sinner, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer lived there on that pale, blue dot. He noted that Earth is a very small stage in a vast cosmic arena and suggested thinking about the rivers of blood spilled by generals and emperors so that they could become momentary masters of a fraction of that dot. He emphasized the responsibility this perspective creates, to deal more kindly with one another, to preserve and cherish the pale blue dot, the only home we've ever known. This perspective challenges the view of Earth as the center of creation, a view that has diminished only gradually over centuries of astronomical observation. Ancient peoples naturally assumed that Earth was unique and central, that the sun, moon, planets, and stars all revolved around our world. The Copernican revolution, beginning in the 16th century, displaced Earth from the center of the solar system, placing the sun there instead. Later observations revealed that the sun itself is not central, but merely one star among hundreds of billions in the Milky Way galaxy, and that the Milky Way is one galaxy among hundreds of billions in the observable universe. Each of these discoveries has reduced Earth's apparent cosmic significance, a process sometimes called the Copernican principle. The idea that there is nothing special about our location in the universe. We occupy no privileged position. We orbit an ordinary star in the outer regions of an ordinary galaxy in an ordinary part of the universe. This perspective, while humbling, is also oddly liberating. It frees us from the burden of cosmic centrality and allows us to see ourselves more clearly as one outcome among many in the universe's long evolution. Yet there is a counterpoint to this diminishment. While Earth may not be cosmically central or unique in its physical properties, it is the only place we know where life has arisen and diversified into millions of species. It is the only place we know where intelligence has emerged capable of comprehending the universe's scale and structure. This makes Earth rare, perhaps vanishingly rare, in at least this respect. The question of whether life exists elsewhere in the universe remains open. The discovery of thousands of planets orbiting other stars has shown that planets are common. Many of these exoplanets orbit within their stars' habitable zones. Some are rocky worlds similar in size to Earth. This suggests that Earth-like planets may be abundant in the galaxy. Whether such planets actually harbor life is unknown. The origin of life on Earth remains imperfectly understood, and we cannot yet estimate how likely or unlikely it is for life to arise given suitable conditions. Even if life is common, intelligent life capable of technology and spaceflight may be rare. The path from single-celled organisms to complex multicellular life took billions of years on Earth, and many contingent events were required. The extinction of the dinosaurs, caused by an asteroid impact, cleared ecological niches that allowed mammals to diversify and eventually gave rise to primates and humans. Had that asteroid missed Earth or struck at a different time, the course of evolution might have been entirely different. The pale blue dot photograph offers no answers to these questions about cosmic rarity or commonality. It simply shows Earth as it is when seen from the outside. Small, isolated, vulnerable. The darkness surrounding that pale dot emphasizes the vast emptiness of space, the enormous distances that separate even neighboring worlds. The scattered beam of sunlight crossing the image reminds us of the sun's central importance, the source of the energy that drives all of Earth's systems and supports all of Earth's life. Voyager 1, the spacecraft that captured this image, continues its journey outward, moving at approximately 17 kilometers per second relative to the Sun. It has long since crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, becoming the first human-made object to enter interstellar space. The spacecraft's power supply, generated by the radioactive decay of plutonium, will eventually fail, probably within the next decade or two. After that, Voyager 1 will continue its silent journey through the galaxy, a message in a bottle carrying information about Earth and humanity on its golden record, though the chances of it ever being found by another civilization are infinitesimally small. The pale blue dot image was not scientifically necessary. It revealed nothing new about Earth's composition or structure. It served no navigational purpose for Voyager's mission. It existed because of one person's vision that seeing ourselves from such distance would be valuable for its own sake, that the perspective it offered had worth beyond data and measurements. Carl Sagan was right. The image has become iconic not because it shows Earth in unprecedented detail, but because it shows Earth in unprecedented context. As one world among many, tiny, against the void, precious because it is our only home. The processes that make Earth what it is have continued for billions of years, will continue for billions more. Continents drift at the pace of growing fingernails. Mountains rise and erode. Oceans open and close over hundreds of millions of years. The magnetic field wanders, occasionally reverses, but persists, generated by convection in the liquid core. The atmosphere circulates, redistributing heat, creating weather, moderating temperature. Water evaporates, condenses, precipitates, flows, sustains. Life evolves, adapts, diversifies, occasionally suffers catastrophic setbacks, but persists and recovers. Species come and go, but the phenomenon of life itself has proven remarkably resilient across billions of years and through multiple mass extinction events. The basic chemistry of life, the DNA and proteins and metabolic pathways, has remained constant even as organisms have evolved into millions of different forms, occupying every available niche, adapting to conditions ranging from Antarctic ice to deep-sea hydrothermal vents. The sun will continue shining for approximately 5 billion more years, slowly brightening as it ages, eventually swelling into a red giant that will engulf Mercury and Venus and possibly Earth. But these changes occur on timescales so long that they are nearly incomprehensible from a human perspective. On timescales relevant to human civilization, to human lives, to the span of recorded history, Earth's basic character remains stable. The seasons continue their cycle, determined by axial tilt and orbital position. Spring follows, winter follows autumn, follows, summer follows spring. An endless rhythm that has repeated millions of times and will repeat millions more. Day follows, night follows day, the rotation continuing at its steady pace, gradually slowing due to tidal friction, but changing so slowly that the difference is imperceptible across human lifetimes. The ocean currents flow, carrying heat from tropics to poles, creating climate patterns, supporting marine ecosystems. The Gulf Stream brings warmth to Europe. The Kuroshio Current warms Japan. The Antarctic Circumpolar Current circles the Southern Ocean, connecting the Atlantic, Pacific, and Indian Oceans. These currents have flowed for millions of years and will continue flowing as long as the oceans exist and Earth continues rotating. The rain falls, the rivers flow, the groundwater moves slowly through aquifers. The glaciers advance and retreat with ice age cycles. The water cycle continues its eternal circulation. Water that fell as rain in ancient times, that flowed through rivers long since vanished, that was locked in ice sheets that have melted, that was drunk by dinosaurs and by the first humans and by us. Cycles endlessly through the hydrosphere, sometimes spending centuries in the deep ocean, sometimes residing briefly in a cloud before falling as rain, always moving, always conserved, the same molecules cycling since Earth's formation. The atmosphere continues its complex circulation, high-pressure systems and low-pressure systems, jet streams and trade winds, monsoons and hurricanes, all driven by uneven heating of Earth's surface by the sun, all influenced by Earth's rotation, all part of patterns that have persisted for as long as Earth has had an atmosphere and will persist as long as it continues to have one. The tectonic plates continue their slow drift, pulling apart at mid-ocean ridges where new crust forms, colliding at subduction zones where old crust descends back into the mantle, sliding past each other at transform boundaries, creating the earthquakes and volcanic eruptions that remind us that Earth's interior remains hot and active. The supercontinent cycle continues, with continents currently drifting toward eventual collision to form a new supercontinent, perhaps 250 million years in the future, which will itself eventually break apart, continuing a cycle that has repeated multiple times over Earth's history. The magnetic field continues to shield the atmosphere from solar wind, preventing the gradual erosion that would otherwise strip away our air over geological time. The field wanders, weakens, strengthens, occasionally reverses, but persists, generated by processes in the core that will continue as long as Earth's interior remains hot enough to maintain convection in the liquid outer core. Life continues to evolve, though the timescales of evolutionary change are generally too long to observe directly within human lifetimes. Bacteria develop resistance to antibiotics. Insects adapt to pesticides. Species respond to changing climate by shifting their ranges. Evolution never stops, never reaches a final state, always continues to produce variations that natural selection can act upon, always remains responsive to changing environmental conditions. These processes, geological and atmospheric and biological and magnetic, all operating on their own time scales, from seconds to billions of years, create the dynamic equilibrium that characterizes Earth. The planet is not static, but not chaotic. It changes, but within patterns. It evolves, but remains recognizably itself. The pale blue dot photographed in 1990 is not exactly the same as the Earth that existed when the photograph was taken, nor will it be exactly the same tomorrow. But the changes are generally gradual. The basic character remains constant. There is something calming in this continuity, in knowing that the fundamental processes that make Earth habitable have operated for billions of years and will continue operating for billions more, that the cycles of day and night, of seasons, of ocean currents and atmospheric circulation and the water cycle will continue regardless of human activity or awareness. That Earth is, in this sense, patient and enduring, resilient to change, while still remaining fundamentally itself. The same sunlight that struck the solar panels of Voyager 1, allowing it to photograph Earth from across the solar system, strikes Earth's surface today, drives photosynthesis, evaporates water, creates winds, warms the continents. The same gravity that holds Earth in orbit around the Sun, that creates tides, that pulls rain from clouds, continues unchanging. The same magnetic field that has protected Earth's atmosphere for billions of years continues protecting it today. The processes persist. And in all this persistence, in all these continuing cycles and flows and circulations and rotations and revolutions, life continues, adapts, flourishes, struggles, dies, is born, evolves, persists. The pale blue dot, seen from billions of kilometers away, contains all of this: the geology and the atmosphere and the oceans and the ice and the magnetic field and the millions of species, all the complexity compressed into a single pixel, all the processes, continuing invisibly, unknowably from that distance, but real and ongoing and patient and enduring. This journey through Earth's characteristics, from the photograph that started it, through the planet's dimensions and atmosphere and water and magnetic field and orbit and life and cosmic context, and back to the perspective offered by that distant view, brings us to the end of our time together. The pale blue dot image reminds us of our place in the universe, neither central nor insignificant, simply one world among many, remarkable for harboring life, for providing the conditions that allowed consciousness to emerge, for being our only home. If you found value in this exploration, if these facts about our world have offered you some perspective or calm or wonder, or simply helped pass the time as you rest, I invite you to subscribe to Nebula Nights. Subscribing helps this channel continue creating content, helps ensure that future videos on similar topics can be made, helps build a community of people interested in the quiet contemplation of scientific facts, astronomical perspectives, and the peaceful consideration of our place in the cosmos. The subscription costs you nothing but a moment of your time, but it means a great deal to the channel's ability to continue. If you enjoyed this, there are other videos on similar topics: explorations of distant galaxies, detailed examinations of other planets, meditations on deep time and geological processes, all created with the same calm approach, the same attention to verified facts, the same goal of providing content that can be both informative and relaxing. Thank you for spending this time here, for listening to these facts about Earth, for allowing me to share this perspective with you. May you rest well, may you wake refreshed, and may you carry with you some small sense of the remarkable world we inhabit, the pale blue dot that is our only home,